Right. So today we're gonna start the lecture with momentum transport. So let me share the screen. Okay. Okay. So yeah. So as we'll know the course syllabus yesterday. Oh, but before that, you can open your EduNext and then you can download uh, the PDF before the PPT or PDF beforehand, so you can have you can write some notes on your board. Okay, right. So anyway, we have 7 people here. 1, 2, 3, 4, 5, 6, 7. Are you all now in Bandung?
I think one of us is still abroad.
Oh, who's still abroad? Helena ya? Is it- who's still aboard? Sorry, my internet looks like I need to change the internet first. Uh, okay. Can you hear my voice? Hello.
Yes, Ibu, we can hear you.
Oh yeah, yeah. So who's still abroad?
I think Helena is still abroad in Qatar.
Okay. Yeah, because we're actually quite we're very small numbers, so I think it is possible if we can do the lecture at the campus. Do you want to do it online or at the campus? What do you think? Or do you want to discuss it with others first? Because maybe you can let's try it. Yeah, let's try have a lecture today, but it is actually much better if we can do it at the campus, and then I can write the equation on board, and then you can try to write it, and then I can go around you and then check your work straight away. Yeah, so you will see that for a transfer phenomena, I think it would be good if we can do it on the campus. But anyway, let me know what would you like to do if you think that being at the campus and then have a face-to-face lecture is better for your understanding. Let's do that. Okay, so right. So now we're gonna start with the introduction of the momentum transport. How to do that? Okay. So this is the reference books that we would like to use. Yeah, the Bird, Stewart, and Lightfoot. If you haven't got that, please try to find one. And we're gonna use a lot of examples and also a step-by-step equation from this book. Okay, so right. Let's consider the momentum transport. Yeah. So do you remember momentum? Yeah, momentum in high school. Momentum, which is mass multiplied with velocity. Yeah. So, oops, sorry. Wait a minute. So this is okay. So it would be. So this is the mass, and also multiply with velocity. So momentum is actually a quantity of unit that is moving. Yeah. besaran benda bergerak. So if anyone or things or human is moving, so they have momentum. Okay, but if you're just you don't move, and then your momentum is zero. Okay, so momentum is a quantity of a moving object. Okay, we can easily imagine the momentum of a solid object. We can calculate the momentum of a car that is, for example, running at 60 kilometers per hour, and we know the mass, and then we can calculate the mass multiplied with the velocity. Yeah, but for the fluids, it also has momentum. For example, a river, yeah, it has a momentum. The what else? The flow of fluids in a pipe. Or for example, a waterfall, or in this case, is the moving of fluids between the parallel plates. That's also there's a momentum, because one of the fluid have a velocity. Okay, so let's have a look. This one. So let's have a look this one, and one very good concept that we know is actually the force is actually related to the change of momentum. I remember when I was in high school or secondary school, I remember there is a quantity called impulse, which is the difference of momentum. I remember there is a impulse, which is F multiplied with delta T, is actually is equal to delta momentum. Oops. So okay, and then so the force is actually correlate to the change of momentum over time, or so force actually correlates to the momentum rate or change of momentum over time. Okay, so if we know why, because we know force is actually mass multiplied with acceleration, and acceleration itself is actually the derivation of velocity to the time. Okay, so then if we put them in bracket, because the mass is constant, we put it inside here. So it's actually the force is actually the momentum, and then the rate of momentum, which is the difference of momentum with the time. Okay, so that means tells you that if we can calculate the rate of momentum, that would be correlate with some force happening to the object. Okay, so the next one now let's have a look at this one. Okay, so we have there are two parallel plates. This is the plate number 1, this is plate number 2. So it's like a two plate. Let me try to find something. Okay, let's say I have these two books, yeah, and then this, yeah, I have these two books, and then this is a parallel plate, and then the plate has a very quite wide area. Okay, and then I put it and then between those two plates, a very large plate, there's two parallel plate, I put some liquid. Yeah, I put some liquid. Okay, can you try to guess yeah, okay, the first one, the liquid that I put it is maybe just water, and I have another two parallel plate, and between those plates I put for example a sauce, yeah, tomato sauce or something. Okay, so yeah, or for example for this one, yeah, in this case, if I have let's say the water inside those two parallel plates, and then I drag one, the bottom one, I drag the plate like that. Okay, so I have these two plates, and then the bottom one I drag the plate. Okay, yeah. Now the question is, what happened to the fluid inside? Is the fluid between the plate, is it gonna be stay still, yeah, or it's just gonna also have a velocity? Yeah, that's the question. Okay, so if we look at here, let's say we have the two parallel plates. This is the upper one, and this is the lower one, and this is the distance between the two parallel plates, which is y. Okay, at t less than 0, the fluid is initially at rest, which is steady, and then just stay still, diam, yeah, Frida diam. Okay, and then when t equal to 0, at a certain time, we have a lower plate in motion. Yeah, this one. We have the lower plate set in motion, and then what happened is the plate will have a velocity of v. The plate will have a velocity of v. Yeah. Then at a very small t, what happened is there would be a velocity built up in unsteady flow. So the area around here, the fluids around this area, yeah, this will also have velocity going up there, because it is being dragged with the lower set of motion. Okay, and at a large t, then there would be a steady flow, where actually we will find that this around this area here, the fluid will be dragged on, and the velocity will be increasing, near to the velocity on the lower plate, while the upper one here, because the velocity, the plate is stay still, then the velocity also, there's the velocity of the fluids here. Okay, this particular profiles, it is happens to laminar flow. Okay, laminar mean berlapis-lapis, yeah, it has a laminates. Okay, so then in the laminar flow, why it's called laminar flow, because we can see layers of different velocity. Okay, now let's have a look on the formula. Okay, so because when we drag this, we drag the lower plate with some force. Okay, with some force. Okay, and the force. Okay, so this is the I drag the lower one. Okay, I drag the lower one. And then when I drag the lower one with some force, then it is happens in the plate that has a area of A. Okay, so then so F divided by A, okay, is actually that would be quite equal. Yeah, so we know that F would be equal with the velocity. Okay, and then if F divided by A, that would be equal with the velocity, and then divided by the y, which is the distance between the y and between the two parallel plates. Okay, so the force should be proportional to the area and also the velocity. So the force should be proportional to the area and the velocity. The force should be proportional to the area and the velocity. So we can put the higher the area, the higher the force. So A we can put it in here, and also the higher of velocity, the higher of force that should be written. Okay, and this F divided A is written as stress. Yeah, so F divided by A is actually, if you remember, F divided by A is actually a pressure, ya, tekanannya, gaya dibagi luas permukaan adalah tekanan, but actually the pressure is actually similar, we call it stress, tegangan. Okay, remember if you remember bahan konstruksi, ya, where is pressure or stress is actually equal to F divided by A. Okay, so this F divided by A, that will tell you about, we call it tau yx. And tau yx is called shear stress, tegangan geser. Yeah, why is shear stress? Because the stress is actually, it is like a drag stress, tegangan geser. Okay, and then the shear stress is the force in the x direction of a unit on a unit area perpendicular to the y direction. Okay, so tau yz is called a shear stress, which is force of y direction, force in the x direction, because force is in this direction, and perpendicular to the y direction. Okay, so this is the area, and the area is perpendicular, tegak lurus, to the y direction. And the shear stress is called momentum flux. Yeah, so the momentum flux is actually, the flux is actually the momentum divided by area. Okay, and then divided by area and also the time. So momentum is called momentum flux. Okay, and this is actually written as Newton Law of Viscosity. Okay, and the quantity that is actually define the real correlation between the shear stress and the Vx to the y is called viscosity. Okay, we call this tau yx, which is the shear stress because of the force into the x and perpendicular to the area of the y-axis. Okay, that one. Okay.
Bu,
Yeah. Okay, Kevin.
For the area, which is the area if
that is
from
good
the
question.
picture?
Yeah, so this area is actually 2 dimension. So in 3 dimension, it's gonna be looks like this, Kevin. Can you see me, or should I close the virtual background then? Okay. Okay, so this one. So this is the area. Okay, there is a 2 parallel plate. Okay, so then this is the area. So this is plate number 1, the upper plate, and then this is the lower plate. Okay, so the area is the area of the plate. Okay.
Okay, Bu. How about when the fluid is already sheared, Bu?
Yeah. Sorry. When what?
When the fluid is already sheared, when the fluid is already like moved, Bu.
The fluid is already in the middle, in the middle between those plates. Okay. So yeah, so maybe
Okay.
I can write it like maybe I can write it like this. There is a plate like that, a large plate. Okay. No. maybe I can write maybe a large, there is a very large, quite large plate, and then there is another one at the bottom there, and between those plate is there is some fluids. So the fluid feels like the area between two plates. It's like a wafer, you know. There is a cream between those.
Yes, bro.
Yeah, like that. And then one of the plate we drag them off. Yeah, we drag them in the sides. This one we have the velocity up there. Okay. Well, this one is diam, yeah, stand still, yeah. So because we have the velocity to that way, of course we're gonna have the force, okay. And then the Newton's law, first in transfer phenomena we have to define the coordinate first, yeah. So let's make it this is the coordinate 0, and this is the coordinate x, and this is coordinate y, and maybe to that area is coordinate z, okay. The three dimension. So tau yx, the shear stress to the velocity of x with direction to y is actually equal to minus mu dvx divided by dy. Okay, so because of there is a difference or the difference of Vx, yeah, the difference of Vx to the y, and then multiply with the mu, and then this called the shear stress. Okay, can you describe?
Okay, bro.
Yeah, okay, right. And then
Yeah. Thank
for
you,
the,
bro.
yeah, okay, so for the units, this is for example for the SI, yeah, international system. So the tau yx is defined as Pascal. Maybe we can just use the SI, yeah? But then you should be able also to transfer into British or CGS if you want. And then the velocity is defined in a meter per second, and then the length, yeah, the distance between the two plates is called m, and mu, if you know the viscosity, is called a per second. Okay, and we also know there is a mu, there's a nu, yeah, this one there, which is called the kinematic viscosity. Yeah, this one is the kinematic viscosity. Yeah, this one is the kinematic viscosity. Okay, so let's now. Okay, any question? Like any other questions about these topics? And yeah, and then this is called the Newton's law of viscosity. So this is the first law that we learn for the momentum transport. Okay, right. Give me 1 minute. I just gonna take a glass of water. Okay, so right, so we know that you've been introduced topics or a concept that is there is a flux, yeah, which is momentum flux, and then it is actually equal to shear stress, and then it's called tau. Oops. Tau. Okay. And then, or maybe I can just okay. So so now the momentum flux, yeah, the momentum flux is actually and then we can, I think I can introduce a term of molecular momentum flux. And then another one is, we call it convective momentum flux. Okay, so what is the molecular momentum flux? Molecular momentum flux is a summation of momentum flux which is caused by a shear force and also a pressure force. So if a fluid, it has a pressure on it, yeah, there is a pressure force, there would be a momentum flux. There would be also a momentum flux. Okay, and if you have a shear force, a viscous force, we call it, it also causes momentum flux. Okay, and that momentum flux is actually the molecular momentum flux. Okay, so viscous force happens when there is a velocity gradient within the fluid. Yeah, when it has the viscous force happens when there is a velocity gradient within the fluid. Okay, and then the pressure force would be always perpendicular to the exposed surface. And then let's just see the following graph in an illustration of pressure and a viscous force. Okay. How to
Bu,
yeah. Yes.
can you explain more about tensor quantity, Bu? I still don't understand even from yesterday.
Which one?
Tensor quantity, Bu. What does it mean, Bu?
Quantity? Sorry, can you explain again?
Tensor quantity, Bu.
Oh, tensor. Oh, tensor is actually vector multiply with vector. It's called tensor. Okay. I think before this, let me stop this screen. Right. Let me share it from my laptops here, and then I think you have to. Okay. Let me share the books first. I think that's better. Okay, so this is the book that we're gonna use, yeah. Okay, so Kevin asking what is tensor and vector. So you can open the appendix A. The appendix A is all the mathematics yet calculus that you need to refresh to understand this one. Okay, this one. So, Kevin, if you remember, do you know the scalar? What is scalar?
Scalar is just the quantity, but no direction.
Yeah, the quantity. Yeah, sometimes a vector multiply with vector in a dot multiplication. Yeah, dot product is actually a scalar. For example, energy. It can be it is a scalar. Okay, and then we also know there is a vector. For example, velocity. Okay, or acceleration, or a force, that is a vector. And then there's also tensor. So tensor is actually vector multiply with vector, and then the product is also a vector. Yeah, so this is a second order vector. Okay, so which one? Yeah. So then maybe for the operation you can later on the tensor there. Yeah. Later on, but so the tensor is actually the vector multiplied by vector. Okay, so have a look on this appendix A to understand the difference between vector and the tensor. Yeah. Okay. Okay, do you remember again about that one? about vector and level?
Kind of, Bu.
Oh,
Ya, kind of.
okay.
Ya, oke lah, Bu.
Okay. Okay. Now let's have a look this one. Okay. So if we have, let's say, let's see this case, yeah. Oh, sorry, not this one. Let's see. Let's try this one, yeah. So this is a point, the point of x, y, z, and this point is in the coordinate x, coordinate y, and coordinate z. Okay, and you're here. Okay, in this one here, these points is actually they will get pressure from all of the yeah, for any it can get pressure. This particle or these fluids can get pressure from any other, yeah, any other sides. Okay, for example, if we look at this area, okay, remember pressure always we have to think about the area. Okay, so here the area which is perpendicular to the x-axis, there would be a pressure there. The pressure we call it P, and then multiply with the Kronecker delta x. So delta so delta, which is we called it Kronecker delta. Yeah, it is just a symbol just to show you that I'll explain in a minute, because it's it is in the next formula. Just anyway, but let's see these points, or let's see these fluids here. The fluids will have a pressure from any other, from all of the area. Okay, so if we consider it, there is on the area that is perpendicular to the x-axis here. Okay, and then there would be pressure, gaya tekan, yeah, so there would be a pressure gaya tekan, and the second one, there would be shear stress or gaya geser. Okay, so that tells you that in any points of the fluids, yeah, for example, with the area with respect perpendicular with respect to x, in this any point they will have pressure from these sides, if there is a pressure, and the second one, they will have a shear stress. What happens is shear stress? The shear stress happen if in this point there is a difference in velocity. Okay, so if we go back in the second one, this is one here. So pressure always perpendicular to the exposed surface. So we have the surface which is perpendicular to the x-axis, yeah, in the graph. So then what would be always there's a force. And then the viscous force would happen if there is a velocity gradient within the fluid. If there is a velocity gradient within the fluid, then that would be a viscous force or the shear stress. Yeah, or this one is called the shear stress. Okay, so so here okay, so this is if the let me say, let's start, for example, this is the point, yeah. If this is this is the fluids, and then this is a point fluid, and in the area of xyz. Okay, this one there. Okay, so we have to consider this from the area with the perpendicular with respect to x, which is this one. And then the area, and then if we consider with the area with the respect to perpendicular with respect to y, yang tegak lurus ke arah sini, ya, they will also get the pressure and also the shear stress or the viscous force. Okay, and if we look at the area around the fluids that is perpendicular to the y-axis, we can also get the there would be a possibility of pressure, that one there perpendicular, and also the shear stress. Okay, so this implies that for just any points of this one of points of fluid in a XYZ coordinate, it will may take, ya, titik ini dapat mendapatkan semua gaya tekan dan gaya geser dari mana-mana, ya. They can get pressure from this side, they can get shear stress if there is any velocity difference, it can get it can get a pressure over here as well, or it can get over there as well. Okay, and this is called the molecular momentum flux. Yeah, and then we called it this one as a molecular momentum flux. This is the momentum flux, which is caused by the molecular gerak molekular, because of the molecular flux. Sometimes in the velocity we can't see it, but you can understand the molecular diffusion if, for example, you have just water, you just have water, and then you put maybe ink, just drip very ink, tinta, and then without any agitation, tanpa ada pengadukan, after a while, then the ink will goes around all of the water. So the way the ink diffuse is because of the momentum diffusion. Okay, in this case it's called the momentum molecular flux because it's related to the velocity. Okay, so the momentum flux is we call it as a Vij. Okay, so Vij is the molecular stress tensor. Why is called tensor? Because it is multiplied with the based on the factor and the multiple factor. So this is called the molecular momentum flux. So this is called molecular momentum flux, and it is actually equal to the pressure multiplied with chronicle delta. What is chronicle delta? So chronicle delta tell you that this value equal to 1 if I equal to 1. I think oh sorry, I think it's not 1, but it should be J. That one there. So if I equal to J, or this one I not equal to J. Sorry, there's a correction there. So this is the pressure multiplied with chronicle delta. So if the I equal to I, which is this pressure is perpendicular to the area, tegak lurus, then you get the number P. While if you have but chronicle delta equal to 0, if I is not equal to J. So if it's not perpendicular, then the P is equal to 0. So this is tells you about the pressure. Okay, and this one, the tau Ij, is the stress, or this is the shear stress. Okay, so this one is the shear stress, or we call it the viscous force. Okay, so that is the concept of momentum flux. Molecular momentum flux is actually based on the pressure and also the shear stress. Okay, so this is formula number 1. Okay, the concept number 1 about molecular momentum flux. Can you think what is the correlation between the Newton's law of viscosity with this formula? Anyone? If you in the previous slide, we know that the Newton's law of viscosity tell you that tau, for example, yx equal to minus mu dvx divided by dvy. So this one, so is there any correlation with this one with the molecular momentum flux?
Ma'am, I would like to try.
Yeah, Christian.
So I think probably the Newton's law of viscosity can be somewhat substituted to the momentum flux equation. Is that correct?
Yeah, that's right. So this actually contributes to this one. Yeah. So like I said that it really depends on the coordinate or the Cartesian coordinate or later on cylindrical coordinate. So if we consider all of the x, y, z, yeah, this is just one component. Yeah? This is just one component of all of them that is side. So there would be tau xx, maybe tau yx, but this is just one contribution of to this one. Okay, so this is actually correlates to the next slides. So you can imagine that if we consider of things, yeah, that is in the x, y, and z, so that means it has a direct normal to the shaded x, then to the y, and also to z. For example, to the direction to the normal x, actually we have the molecular momentum x, we call it. This is the bold one, tanda tebal. That means actually the tensor, yeah. And then this equal to P, which is the pressure multiplied with chronicle delta, and then this one tau of x. Okay, and in this shaded x, then we can break it down again to the x component, to the y component, and also to the z component. Okay, so there would be we call it Vxx equal to P plus tau xx, and then Vxy equal to tau xy, and then Vxz equal to tau xz. Why there is no P in here? Because the P is actually the chronicle delta, because this is x with y component. That means I not equal to j, so then there is no pressure in that one. Okay, so there would be no pressure, so that's equal to that one there. Okay, and then if we consider with the direction to the shaded face, which in the y, then we have another 3 sets again of the components, and then with the z we have another 3 sets of components. So there would be in total there would be like 9 breakdown of the molecular flux momentum. Okay, so why did we call it molecular momentum tensor? Because they are associated with the molecular motion. So they move it because there's some something that associated with the molecule. Okay, if you get pressure from the molecules, then the molecule then it will have the momentum, yeah, because it is moving, akan bergerak. Okay, if you have a difference in velocity, you can also get the viscous force, and then it help you moving again. And then when the molecule have a velocity, then it will result in the momentum. Okay. Yeah, questions please.
Oh, I have a question.
Yes.
Why is it when I is equal to j, there is pressure, but if it's different, there is no pressure, or it's the other way around?
Yeah,
It's because of the Kronecker delta. Why is it that way?
because here's the thing. So chronicle delta, this one, yeah, the delta here, this is tau x. Sorry, the chronicle delta x, and the chronicle delta x also have three different component, yeah, xx, xy, and xz. So this one here, it should be x and x, so it should be in the right direction in order because the pressure should be uh, perpendicular, harus tegak lurus. Okay, so if you have this chronicle delta, which is I is not equal to j, that means the pressure is not perpendicular to the area. Tekanannya tidak tegak lurus dengan area, sehingga tidak dimasukkan ke dalam, tidak bisa diperhitungkan. Okay, so the pressure that we consider is only the pressure that is perpendicular, yang tegak lurus with the area that we're looking at. Okay, so in this case, for example, the component of the forces with, for example, with the direction normal to x, if it is to the y component, so that is not perpendicular, so then we don't consider the pressure, because the pressure that we need to consider is only on the same direction. Later on in examples, I think you can have more description about what I'm talking about. Yeah, let's see. All right. So this one is called the flux, molecular flux momentum. The flux momentum which is caused by the molecular motion. Jadi flux momentum yang disebabkan oleh gerakan molekul. Gerakan molekul disebabkan oleh satu gaya tekan dan gaya viscous. Okay, so the molecular flux momentum is when there is no velocity. There's velocity. It is only associated with the molecular motion. Okay. So for example, the in this one, maybe I can go back to here, this one, yeah. So in this case, it is called molecular momentum flux because we have a velocity over here, yeah, we have a velocity over here, but then the molecule is stand still actually, but because of there is a difference in the velocity between this one and that one, then there would be differences in velocity, and because of there's a difference in velocity, there would be a shear stress, gaya viscous. Okay, and because of the gaya of the shear stress, then would be molecular momentum flux. Okay, so that is the difference for the molecular momentum flux. Okay, the second one.
Sorry.
Okay, Christian.
Ma'am, so I just want to confirm something. Please correct me if I'm wrong. So basically, what causes shear stress is actually a certain force, and momentum, and sorry, what is it? And molecular momentum flux is caused by shear stress. Is that correct, ma'am?
Yes. So molecular momentum flux is caused by, it can be by shear stress or it can be by pressure. Yeah. Okay.
Okay, ma'am.
Yeah, this one in this case, in this slide, we only talk about the shear stress, yeah, for this one. But the larger one, then here we can consider there is a shear stress, this one, and also there is a pressure. Okay.
Ma'am, so does shear stress always correlate with the pressure? So I mean,
no, it's different thing. It's different thing. So sometimes later on in some example we can consider when we can think that there is a pressure in the system, and then we can neglect the pressure. Okay, but usually there's always shear stress. Yeah, it's actually it is in different problems, different topics. There would be some different what we call it boundary conditions.
Oh, I see, ma'am.
Yeah. Okay.
Ma'am, could you go to the next slide? I want to ask something again. Sorry.
This one.
Yes. So does this correlate with the when I learned in physics? So it's basically, for example, if I multiplied by I is basically equal to 1, so that's 5 in the when x when it complements to the same direction, so that's why the pressure is available.
Yes.
Is that correct, ma'am? So basically, it's actually the multiplication of the same factor. Is that correct, ma'am?
Yeah. That's right. Yeah. So
But
this is based. So actually, this one, yeah, this is actually tells you that if phi xx actually equal to phi chronicle xx, like that, right? So p multiply with chronicle delta xx plus tau xx, right? This one. And because the chronicle delta I equal to j, this one, yeah, I equal to j, so then this value become 1. So that's equal to p plus tau xx. Is that where you?
ma'am, but why is the pressure minus, ma'am? Where is the pressure negative?
No, it's not negative.
Oh, it's equal. Sorry, ma'am.
No, it's not negative. No.
Oh, sorry, ma'am.
Yeah, it's positive.
Oh,
Okay, so maybe I'll write again. So this would be Cxx equal to P multiply with chronicle delta xx plus tau xx. This is called the molecular flux momentum x, yeah, at the velocity x to the direction of x, ya. So this apa ya, bahasa Indonesianya ya, flux momentum ke arah x yang disebabkan oleh kecepatan ke arah x. Yeah, so the molecular flux momentum which to the direction of x, which is caused by velocity to the x. And this is tell you that, okay, so the chronicle delta is xx, and chronicle delta xx is equal to 1. Yeah, so then it become p, and then this and then tau xx is actually shear stress caused by velocity of x to the direction of x. Okay, I think I need to write it down, yeah, so you can write it down, this one. Okay, so for example here, so for example tau yx is the force in the direction of x, yeah, per unit area perpendicular to y direction. So the first one, the first letter tells you the direction of the shear stress. Okay, arah dari tegangan geser, arah dari shear stress. Okay, and this one is the difference of the x, the difference of the velocity that causing the x. Okay, or maybe I can write it one by around here. Where is it? For example, so tau yx is the shear stress to direction of y, okay, caused by difference of velocity x. Okay, I think that would be okay, because it is so the first one, okay, see, so the first letters tells you about the dy, or which is the direction, yeah, the direction of the perpendicular to the that one there, and then the x is actually tells you about the the direction of velocity. Okay, maybe you can write it down, or do you want to write it down?
Yes, ma'am.
Okay, so okay. Okay, let's try to move on. So this is the molecular momentum flux, and then you will find this a lot, and then later on we can consider if there would be always shear force, and also if there is a there is a pressure, then we can accommodate this one. Okay, the next slide, even though it is looks like a very while this looks like very complex, but later on you will see that in the problems, not all of these components is available. Yeah, so the next steps is we have to identify which one that has a value yang ada nilainya, or which one is there is no value. Okay, why? For example, tau xx. Yeah, the tau xx is actually caused by the difference in the velocity to the x, for example. Okay, and then the stress should be in the direction of x. Sometimes we can't get this one. Yeah, sometimes we don't have different velocity in x. So sometimes the tau xx it can be 0. Okay, so later on, just be patient. So it may be I don't know, maybe next week, or if we have time, I can give you some examples. Then we can try to find which one is the one that has value, and the one that doesn't have value. The kucing. Okay. Okay. Next question. Okay. Now let's check the next concept. The next concept is called convective transport. Okay, the convective transport, the convective flux momentum, it is caused by a velocity or by the bulk flow. So that means when the fluid have a velocity, like in the river, in the pipe, the fluid that is flowing in a pipeline. So the momentum is only the momentum can be transported by the bulk flow of the fluid. Okay, so and this is called the convective transport. This can we need to consider this one if the fluid that we're looking at is in motion, ya, sedang bergerak. For example, in the river, for example, the fluid is also moving inside the pipelines. Yeah, that would be should be considered. Okay. And then the velocity is actually a function of distance, and then for a Cartesian coordinate, it would be a function of x, y, and z. Should be z, yeah. And then also with the time, okay. And then so this is the vector, yeah. The vector equal to the vector function of time, x, y, and z. Okay, and if we consider a steady state, which is not a function of time, then the momentum flux, it can be a component of x, y, and z, and that should be written as this one. Okay, it is written by rho, yeah, because rho. Okay, rho is it is actually based from this one. So because the momentum is m multiplied with v, yeah, and the v is actually m is actually the rho, yeah, the density multiplied with the volume, yeah, volumetric rate multiplied with v. Okay, and the volumetric rate, so this is momentum, yeah, and then momentum rate. Okay, and then that would be equal to rho multiply with the area multiply with the length, yeah, and the length we can call it, for example, the v, small v. This one is volume, yeah, and then multiply again with the v. Okay, so this is the momentum rate. So the momentum flux is actually equal to the momentum rate divided by area. Okay, momentum rate divided by area. Okay, and then the area we cancel out, this one, yeah, we cancel out, so that become rho multiplied with v multiplied with v. And this v is actually it consists of vx multiplied with vy and then also vy and also vz. Yeah, there would be that is the component. So then it become that one. Okay, so the component of the momentum flux now there's rho vx v and then rho vyv and also rho vzv. Okay, so here we can this is how we write it. Yeah, this is the convective momentum flux also in if we just consider one point and then we consider again, because it has to we have to consider the area that is perpendicular to the direction of the momentum flux. Then here is the formula rho vxv. This one is rho vxv, and also this one rho z. Okay, and then if we break down the vector again, there is the component is vx, vy, and vz, and then you can see that it can be I think it should be okay, looks like I have to close it down. Yeah, this should be yeah, it should be, yeah, this one. Yeah, so that would be it's not that should be the component x, component y, and component z. I didn't write the component z, but anyway, that should be a component z. There's a z component here. Yeah, it's not, it's look like crop. Sorry, the picture is cropped. So that would be the flux momentum through the shaded surface. There's a vxx and then vxy and so on. Okay, so anyway, so the combination between molecular flux momentum and the convective flux momentum is defined as a combined momentum flux. Okay, so in a sense, I think we can simplify them to become, we call it combined momentum flux. The combined momentum flux is, we call it psi, yeah, psij, psij. Okay, so this is combined flux. And then this one is contributed by the velocity, the convective, yeah. To flux, and psij, which is psi ij is the molecular. Okay, so the combined momentum flux is actually correlated with the convective momentum flux plus molecular momentum flux. And then if you want to break down again, the molecular momentum flux is defined as the pressure, gaya tekan, and also the shear stress or the viscous force. Okay, and then so this is the one formula that we need to looking at, yeah, the formula that looking at this one, which is the combined momentum flux equal to convective momentum flux plus the molecular momentum flux, where the molecular momentum flux equal to the pressure and the shear stress. Okay, so that is the end of the first slide, the first presentation. Okay, any questions? But
Ma'am, I have a question.
Yeah, okay.
Could you go back to the convective momentum transport slide?
This one?
Before this one, I think. Yes. Could you explain again about the correlation between momentum rate, volumetric rate until it becomes momentum flux? I still don't quite understand that.
Oh yeah, okay. Maybe let's just write it here. So we know that momentum is equal to m multiply with v, yeah? You right? Okay?
Yes.
Yeah. Okay, so and this I think, and then this momentum is actual to rho multiplied the volume with multiply with v. Okay, so this is kecepatan, ya. This is the velocity while this is the volume. Okay, now because we're in the fluid, so we have to talk about momentum rate. Okay, which is rho multiply with the volumetric rate. Okay, multiply with v. Okay, now if you consider this kind of x, y, z, yeah, let's say I have a block of fluids around here. If, for example, this is the area and this one is moving, so to get the volumetric rate, it should be velocity multiply with the area, right? So this volumetric rate is actually equal to rho multiply with the area of the perpendicular one, yeah, of this fluid that is moving, multiply with the v, multiply again with the v, because v is actually apa ya, distance divide time, yeah. So if area multiply with distance, that's gonna be a volumetric. You can check with the unit, yeah. M2 multiply with M become M3. Okay, now flux, any flux is called the rate divided by area. So any flux, heat flux or mass flux or momentum flux, so rate of the quantity divided by the area. So momentum flux is actually the momentum rate divided by area. So the momentum rate in this case is this one. So the rho multiply with the area. Just try to find this cube, yeah. Just to an example there. Multiply with the velocity. Multiply with the velocity and divide by those area. So that become rho v. So that is the momentum flux, which is caused by the convective movement. Okay, so what do you think?
Ma'am, I want to ask and clarify something.
Yeah.
So before I was wondering, why can't v become like v square? So is it because the v is coming from different directions, ma'am?
Yes, yes. It become a different direction. Why is not the v square? Good questions. Because if we look at the next stage, later on it can be become v square if you want. But the thing is, each v has parameters, yeah. this V is a vector, right? And in any vector that will become there would be the parameter, yeah, the direction for that one. It can, yeah, there is a x, y, and component. Okay, so if you consider this one, why I can make it V square, because this has 3 components and this has 3 components, so you have to consider 9 component. Yeah.
Oh, I see, ma'am.
Yeah.
Thank you.
Okay. All right. I think that's the end of the slide. I would like to move to the next stage. Let me check. The second one is the convective flux. Oh, this one also we finished that one. Okay, and then let's see now. Now maybe we can go to the next start. Yeah. Okay. So the question is, why we have to be really detailed in describing those momentum flux? Yeah. What is the the use of that? So we're gonna set up. We call it shell momentum balance, and this shell momentum balance. Wait. Give me a second. Right. Okay. The thing is, with the shell momentum balance, we're gonna set up a balance. Looks like close to mass balance, seperti neraca massa ya. And this the shell momentum balance will tell you about the and then in this shell momentum balance we need some equation, and then the flux momentum is one part of the components that we're gonna looking at in the momentum balance. Okay, so the learning outcome for these topics is wait. Okay, so the learning outcome is actually we know how to set up a different momentum balance, yeah, and then we understand how to obtain a velocity profile of the laminar flow of fluids in a simple system. Okay, so before that, we have to understand also. So in transfer phenomena in a modeling, we will start, and then I think you will find this a lot, yeah, even in your research or in many real problems. Sometimes we can't really we have to start with a very simple system. Okay, with that simple system we can understand, we can model the system, and then we can understand the system, we can get information from that our calculation, and then we can understand something. And then once we know that, okay, so let's move on to the more complex system, and then try to do that one more. So yeah, so that is that's why in the transfer phenomena we're gonna really start with a very simple system. Okay, so this is very interesting, yeah, because so the concept of simple system that we're looking at is, first, it is steady. So it's steady, so there is no time included. It's not transient. If you're if you're interested to go to the master degree, it will be introduced with a transient system, or where the system is changing within the time. Okay, so for example, I have you have the reactor, and then you want to know the composition of the reactant and the product in the reactor within the time, at every time, and how it's changing is called a transient system. But in this case, we just gotta think that it is a steady, and then we don't consider the time because it is steady and then everything is just in a steady way. The second one is the laminar flow, which is I explained to you before that each laminar means it has a layers, ada lapis-lapisnya, yeah. So and then you know already that we can calculate laminar flow using Reynolds number, and then the properties is considered a constant as well. Give me 1 second. Okay, so this one is the this is an example experiments, yeah. So there is a flow, there the fluid flow, and then in one point we put a tiny hole there, a tiny pipe, and then we put maybe a fluid containing particles, maybe in different colors or something. Sorry, it is very noisy. Okay, it is very so then that means that if we put this one here, then the ink, yeah, or the fluid containing these particles will, if we track them, it just will go in layers. Okay, so the laminar flow in which fluid layers move smoothly over one another in the direction of flow. However, if you have a very high velocity and it becomes turbulent, and just in an instant, these particles will be just spread it out, and then that would be swirling, and then the flow pattern is complex and time dependent, and then considerable more motion perpendicular to the principal flow direction. So this is a turbulent. We don't consider this one, we consider the laminar flow. And then another one that we considered is actually the properties is considered constant. So the property that we're kind of looking at is we're kind of looking at about the mu, the viscosity, and also rho, yeah, that we're gonna use, and also the temperature is all constant. In some cases, the viscosity can change. For example, in the non-Newtonian liquid, or in a slurry, or in a your hot sauce or tomato sauce, yeah, it can change. The sometimes in some case density can be changing as well, but we don't consider that one. And also if there is a heating or something, sometimes there would be a change in density as well, but we don't consider that one. So we consider all of this is actually constant. Okay, so this is the most important one. Okay, so the shell momentum balance is actually the law of conservation, yeah. Not conversation. Okay, wait. This should be conservation of momentum. Okay, so they tell you about the conservation of momentum. And then in a system which is defined space and time, we can construct a momentum balance. For a steady flow, so we have to think, it is similar with the momentum convective in, rate of momentum in by convective transport minus the momentum out by convective transport is equal plus the momentum in by molecular transport minus out by molecular transport, and plus the gravity acting on the system should be equal to 0. Okay, so you can try to imagine this one, or it's actually, we also can write that rate of momentum in combine, yeah, minus rate of momentum out plus force gravity equal to 0. So if you consider this one, it can be C, yeah, Cij in, and also minus Cij out. Okay, so you can consider from C, you can consider from the combined momentum, or if you want to break down with the convective one and the molecular transport, it's just fine. This is all similar. Okay, now how to solve setup and solving the procedure. Okay, the first one that is very important is we have to consider the non-vanishing velocity component. Okay, remember, if we have the velocity, yeah, for example, we have velocity only to the direction of x. Okay, what is the velocity to the direction of y? Okay, for example, in the problem, I know that the velocity is only it happens on the direction of x. What is the velocity to the direction of y and z?
0, Bu.
Yeah, that one. Yeah. So you have to you should be able to identify which one is the vanishing velocity component and also the non-vanishing velocity component. Okay. So if because if you have velocity to the x, it's only go that way. Yeah. If you have velocity to x, y, and z, maybe it would be like swirling, something like that, ya. Akan jadi kayak muter-muter. Okay, so then if you have a velocity of x, then you can say that, okay, so the v y equal to 0, then vz equal to 0. So then all of the equation previously that I wrote before, there are 9 equation or something, some of them can be cancelled out. Beberapa bisa dihapus because the sum of the velocity is 0. Okay. So first later on we have to identify the non-velocity components, and the second one, let's write a momentum balance on that form, the previous one, using a thin shell perpendicular to the relevant spatial variable. So we're gonna describe the thin shell. All of this in the exam is actually syarat lulus, So from the identifying the coordinate, mulai dari menentukan coordinate, that is syarat lulus. Okay, and then let's make a thin shell, and then once we calculate the equation, let's the thickness of the shell approach 0. So if the delta of the thickness approach 0, then we can approach limit. Limit of the delta x, for example, equal to 0, that would be a differential. So then we will have a differential equation for the flux momentum. Okay, and then once we have the differential equation, then we can integrate this equation with the corresponding boundary condition, to get the momentum flux distribution. And after that, from the momentum flux distribution, we can insert Newton's law of viscosity to obtain a differential equation for the velocity. Okay, and we can use the velocity distribution to get other quantities, for example, the maximum velocity, average velocity, or the force on the solid surface. Okay, so let's have a look one by one. So now the very important one is the boundary condition, kondisi batas. Okay, so the momentum balance is a differential balance, so it would form a differential equation. You may need this one, so you have to maybe try to remember or know where it is. So this is all the commonly used boundary condition. So at the solid and fluid interfaces, the fluid velocity will equal to the velocity in which the solid surface is moving. For example, on the plate, we have the plate, yeah, we have the tube plate, or maybe let's write it just without 3D. So for example, in a parallel plate, okay, if this one have v to the x, yeah, with this velocity, wait, close the door again. Yeah, with the velocity this one, then the fluid velocity at the solid interface, the fluid velocity would be equal to the velocity in which the solid surface is moving. So around this one, the fluid's velocity around this area, that would be equal to this velocity. Okay, so that is the first boundary condition. Okay, the second one, at the liquid-liquid interface of a constant x, it is we actually we seldom use this problem, but for example, we have water and also the oil, yeah, around the solid liquid interface area, the component v x, vy and vz, it would be continuous through the interface. Okay, all the component is continuous. And then this one, this is also very important, at the liquid gas interfacial plane. Okay, so the tau y and tau z would be taken to be 0. So this one, for example, I have a, maybe we can go back this for the next part. For example, for between the liquid and gas, you have, for example, you have water and also just atmospheric pressure. Maybe I can write it here, yeah. For example, you have water flowing, yeah, this is water flowing, okay, and this is atmosphere, gas, this one, yeah. So the tau xy, so the tau xy around this one, tau xy and tau xz would be equal to 0 at the surface of the water, because at the gas and liquid interface, the stress tensor component would be taken to be 0. Okay. That would be some of the boundary condition. I hope you can go back to these slides, or that's also in the books, and then we can check again sometimes later on. We can if it is applicable to our problems. Okay, now we still have about 20 minutes, so I think I can explain an example about the falling film. Yeah, the very maybe let's go to the next slides. Okay, let's try to see the next slide. Okay, maybe it is much better if we can try to imagine with this example. Okay, you can also find this example on the book. Okay, so this is a typical example of momentum phenomena. Okay, so here I have a flow of a falling film. I have a reservoir in. Okay, I have a reservoir in around here, and then here there's an overflow, and in this overflow that the liquid will falling. Okay, with some thickness. Yeah, there's some thickness, and then we consider L, the length of L. Okay, the disturbance at this area and this area we neglected, so we only consider the L, this one. Okay, so the first one is we have to find the coordinate. Okay, so we have to find the coordinate. Which one is the coordinate that we're looking at? Okay, okay, the first one we have to find the coordinate there. So the coordinate that we're gonna looking at, we can start with these points. Okay, so this is the coordinate. We can write this at z, so this can be this one. Yeah, this coordinate is the this to the respect to the x. Okay, and this area is to the z. Okay, so that one there, and this is disturbance at the edge of the system, z equal to 0 and z equal to L. So this is actually z equal to 0. This is would be z equal to L. Okay, and this one is the x equal to 0, then, and this one, for example, x equal to, I don't know, delta, for example, the thickness of the film. Okay, and then the area, the wide, yeah, the width is W. Okay, that one there. Okay, so then what we need to know, we have to make a thin shell, bikin cangkang tipis, ya. The thin shell that with the maybe around the thickness of delta x. Okay, so what we will do is we're gonna make a very thin. No, it's too. Or let's write it one by one, or can I make it bigger? Okay, let's make it bigger then. Yeah. Okay, so this one. Okay, so I will write it from. So this is the. I will start 0 from here. Yeah, from the surface. This is the x. This is the z coordinate, and the y coordinate is the width, ya, lebar dari liquid film. Okay, so this is actually when z equal to 0, and this is when actually z equal to L. And then we have to make a thin layer of shell. Okay, and then we can maybe write the thin shell maybe using thin shell like that. And this thin shell has the thin shell has a thickness of delta x. Okay, and then let's make it into a 3-dimension. That would be looks like this one. Okay, I think I have written this one before, so I have to delete it first. Give me 1 second. Yeah. Okay, so and then we put it into like this one. Okay, this is the shell, the thin shell. It started with x, yeah. It started with from x to x here, and then it ends with x plus delta x, and then it starts with the z equal to 0, and then z equal to L. Okay, so you can imagine a very thin wafer there with the delta x of the thickness, and then the width is w, and then the length is the l. Okay, but before that, we can try to find okay, so some notes on the phenomena. We can expect that the viscous force will prevent continued acceleration of the liquid down the wall. So the Vz would be independent on a short distance down the wall. So we can postulate that first the Vz would be only a function of x. Okay, so here if you look at here, that would be because of the gravity, there would be a flow of the Vz. Okay, but the Vz what we know is only a function of x. Yeah, which means maybe the one that near the surface, the Vz would be faster. Yeah, but the Vz near the V arah Z, yeah, Vz near the plate would be quite low because there is a resistance there. Okay, so the Vz around here would be similar with the Vz around there. Okay, so the Vz around Z equal to 0 would be equal to Vz equal to L. Okay, you can find it so it doesn't so the Vz doesn't increasing. Why? Because it is in a small direction, and then with the mass balance you can actually find that Vz in particular x here would be equal to Vz particular there. Okay, so then it is written by Vz equal to Vz function of x, only function of x. Okay, so that is some notes. The second one, so then we postulate phi is a only function of x, and then Vz equal to 0. And do we have Vx? What do you think? Do you have Vx? Do you have Vx? Yeah.
The thickness of the sand, right? Wait,
Do
no,
we
yeah.
Do we have Vx?
No, I don't think so, Bu, because
I
the
think so.
thickness does not increase, right?
Yeah. Wait. Do we have Vx? Why it is 0?
Because the thickness of the sand does not increase. Bu.
Because if you look at here, the flow is on the z direction, yeah, isn't it? So z direction, that means from here to here. Okay, do we have flowing a flowing fluid from to x masuk ke sini? Nggak ada ya?
No,
Okay, so then we don't have v x, yeah, v with to that one there, because the flow is only to the flow is only to the respect to x and to the z, yeah, the flow is only respect to this z, but no flow going to that x direction. X direction is this way, yeah. Okay, so that's right. So then we can also write the Vx equal to 0. Okay, and also P, do we have pressure?
Yes.
Yeah, we have pressure, of course. The pressure comes from the atmospheric pressure. We have pressure, but the pressure is only on the direction of x. So karena tekanan atmosferik ya. So that direction and also that direction, yeah. So the P. Okay, so the P is so I think I can write it here. So P from atmospheric, and it is only function of x as well. So if you think about it, with the atmospheric pressure and then with function of x, so it's because of the hydrostatic pressure, yeah, hydrostatic pressure. But if we consider that between similar x, then the P would be similar. Okay, now the non-vanishing component, yeah, the non-vanishing component of a tau. Or later on, we also need to consider what is the non-vanishing component of tau. Is actually the tau z later on, but I think we can find this later on. Okay, now so let's consider this one. So here, this is the shell thickness in 3 dimensions. So you can draw in 3 dimensions, or you can draw in 2 dimensions. Yeah, it's up to you. So if I can draw the 2 dimension would be like that, maybe. Yeah, a very there. That would be also, for example, this is z equal to 0, z equal to L. Okay. And then we have to consider all of the momentum that may happen in this area. Okay. First, we have from here to here, yeah, because this is the direction. We have CZZ. Yep, CZZ means the combined momentum to the z direction caused by the velocity in the z direction. Okay, so here we have tau ZZ in. Yeah, from the outside we have CZZ out. Okay, so you have the ones that in and the ones that out. And then if you remember, the CZZ equal to the this one is from the molecular flux P plus tau ZZ, and then rho ZZ. Okay, so if you're wondering what is tau ZZ, yeah, so tau ZZ from the Newton's law is actually equal to I think for the formula we can open the which one there? What there? Okay, we should follow table B1. So I think let's have a look on the table B1 there. I think I have to close this one and let me share with the other book there. This one, yeah. So we can find also the formula on the appendix B1, yeah, and appendix B about the Newton's law of viscosity. So in the previous one, we wondering what is tau ZZ, what is tau XX, for example. So we can consider this one. So in the in the appendix B1, the Newton's law of viscosity, you can say that this is the formula of tau XX and this is the formula of tau ZZ. Sometimes we can neglect it the second one, yeah, because this is like a formula or something. So it sometimes this calculation can be omitted because the fluid can have constant density. So just ignore this one. But then we understand that minus tau ZZ equal to minus V to dou VZ over the dz. Yeah, this one. Okay, can you write down? Yeah, can you write it down? So this is tau ZZ. So in our case, do we have tau ZZ? Do we have the difference of z with respect to z?
Yes, I think.
Yes or no? So this is the z, yeah? So the z is changing with respect to z. Is z in z equal to 0 equal to the velocity in the z equal to 0 equal to z equal z in the L? What do you think?
It's the same, right, Bu? You said it's the same.
Same?
The velocity.
Yeah. How about others? Fatia, what do you think? The velocity of z at z equal to 0 and velocity of z at z equal to L. Is it the same or different?
I think it would be different.
Okay, once it's different, one is the same. So which one is right? Okay, right. Okay, let me write this one so I can let me share stop sharing, and then let me write it again in the at there. Okay, so based on that one, okay, yeah, let me write the formula again. So the formula is tau zz is equal to minus mu 2 dou phi z divided by phi dou z. Okay, so what do you think? Is it similar or not? Do we have dou phi z over dz? Okay. Okay. If you look at here, so the phi z is only a function of x. Okay. So phi z is only a function of z x. So that means phi z is not a function of z. Jadi dia tidak berubah kalau panjang z-nya berbeda. Okay, so z will be come independent of z short of the wall. So this tells you that z in here, yeah, z at equal to 0, the velocity of phi z in the equal to 0 would be equal to phi z equal at z equal to L. Okay, so the velocity is not changing with respect to z. Kecepatannya tidak berubah terhadap z. Okay, so because of that, then we can conclude that dv over dz, is that 0 or not?
0.
Yeah,
There's no change.
so that would be equal to 0. Okay, so then phi z tau zz would be equal to 0. Okay, another one. Let's say for example, maybe with different color, yeah. I would like to know, try it, if tau, for example, tau yz. The tau yz is actually minus mu d phi z divided by dy. Okay. Is it 0 or not? Do we have a difference in phi z to the y?
No, Bu.
No, yeah, because we know that the phi z will be changed with x, not y. Yeah, in this one, it's only a function of x. It's not function of y as well. So the one that apart with the length, the width is also the same. Okay, so because this is equal to 0, then the tau yz would be equal to 0. Okay, so the tau yz would be equal to 0. Okay. So if you think about it here, there would be some a component that would be actually cancel out. That would be equal to 0. So can you try? Can you make it? Can you try which one is equal to 0? For example, tau zz. Is it 0? This one, yeah. So for example, this one. Sorry. Wait. Wait. Okay, for example, tau ZZ, is it 0? This one?
It's 0.
Yeah, this
Yes.
one is 0. Okay. Um, how about tau xz? There is tau xz, and how about tau yz? That would be equal to 0 as well. How about this one? Rho phi z, rho phi y phi z. Is it 0? Phi y. Do we have phi y? Phi to the direction of y?
No, Bu.
No ya, tuh ke arah w nggak ada ya, right? From 0 to this side, we don't have any difference. We don't have a difference of the velocity up here. So this would be equal to 0 as well. Okay, so then so that's how you identify the vanishing, non-vanishing component. So later on, then you can find quite a similar one. All right, looks like you can I think in your spare time you can have a look, try to find this one. I will continue again on Thursday. Yeah, is it Thursday or no on Wednesday next week to try to finish this off about this formula. So later on, just a glance of this. Basically, later on we have to calculate the momentum, yeah, the momentum, but the momentum flux, yeah, momentum flux, because it's still in the flux, which is divided by the area, so we have to calculate it with the perpendicular area. So that's why here we consider the area there is a W multiplied with delta X and so on. This tell you the momentum flux multiplied with the area, and then that's equal to the rate of momentum. Okay, and then once you know this momentum here, you can try to find which one is equal to 0, for example, and then which one they have the value. Okay, and then here they make into the limit as well. They make into the limit, so the thickness become the limit, and then once you get the limit, then you can get a differential equation. Okay, and then once you get the differential equation, you will have to integrate, yeah, and then once you to get the integration, you need a boundary condition to get the constant, yeah, and then once you found that, you will find the momentum flux distribution. To get the momentum flux distribution, you will find to calculate again the velocity distribution. Okay, so have a look in your time. Next week I will continue with these topics again to try to calculate with the mathematics. So, and then also we introduce also the cylindrical coordinate, yeah, the cylindrical coordinate regarding the flow in a pipe, and also with some others examples. All right, I think that's all from me. So I'm sure this is quite new for you. So just try to understand in your spare time, and then check with some, I think, ask with your friends as well. Or and then as again, the recording would be uploaded during the weekend. Okay, everyone. Maybe any other questions before this? Okay, just suggest that to mention that in exam all of this step is very important. Yeah, that's why when I try to give you the lecture, I'm gonna be very slow if it's still not slow, or maybe to just to ensure that you should know the each steps of the how to do the calculation. All right, everyone, thank you very much for listening, and then I'll see you again next week. Thank you. And then who is the class coordinator? Is it Dama again or different? Who is the class coordinator for this transfer phenomena class? Hello? Or Kevin, yeah? Kevin, can you be the class coordinator?
Yeah,
Yeah.
sure, Bu.
Okay, yeah, okay. And then please tell me later, do you consider, so you know this kind of lecture, yeah? It is really, you have to write it by your hand, and then you really step by step. So try ask your friends if are you interested to be to have this one on the class. Okay, but and then but still it's still hybrid, so it's still gonna be recorded, and then we use those smart the smart whiteboard from the campus, so it's still gonna be recorded. So please let me know if you think you're interested to have this on the campus, then I will arrange it with Pak Kaprodi to arrange it for you. Okay, everyone.
Question.
Yeah, Fatia.
If we have it offline, will the one on Wednesday also be offline or just the one on Friday?
I think the one on Friday. So because it's 2 hours.
Okay, thank you very much.
Yeah, yeah. Is it? I think, and also on Wednesday you also have lab tech, yeah. Right. So.
We have lab tech from
Yeah,
9.
so that's why maybe it's very short time, around 50 minutes. So I think we can do it on. The thing is, we can maybe we can I can explain the concept on online like this, and then we can use those 2 hours by a lot of practice, and then I can go around with you, and then yeah, check sit with you and check the calculation one by one. I think that would be better. Yeah, that would. But yeah, just tell me, yeah, tell me what you think about it. Okay. All right, everyone. Thank you very much, and have a good weekend. And then I'll see you again next week.